So we're going to talk about irreducible characters. We can define a Hermitian inner product on the vector space of complex valued class functions on G by alpha inner product with beta equals 1 over the size of G times the sum over all elements of G of alpha of G times the complex conjugate of beta of G. And one of the key results in elementary representation theory is that under this inner product, the irreducible characters are an orthonormal basis for the vector space of complex class functions on G. And this is a useful fact. For example, we can use it to show that the number of irreducible representations of G equals the number of conjugacy classes of G. But why are the irreducible characters orthonormal, and why are they a basis? In this video, we present a proof that's intended to shed some light on why the irreducible characters must be an orthonormal basis. Let's start with orthonormality. Suppose that V and W are any two representations of the group G, and consider Hom V, W. By definition, this is the set of C linear transformations from the vector space V to the vector space W. So this has nothing to do with representation homomorphisms. These are just linear transformations from V to W. We can identify Hom V, W with the tensor product V star tensor W. So V star is the dual space. It gives us functions from V into the field, and from there we send those scalars into W. So this gives us a way to describe elements of Hom VW, and this applies anytime V is finite dimensional. If V and W are representations of G, then these vector spaces are also representations of G. And because they are isomorphic representations, the characters of these two have to be the same. So let's look at the character on the right side here. First of all, if V is a representation of G, then the dual representation V star has character equal to the complex conjugate of the character of the original representation V. And we know that the character of a tensor product of two representations equals the product of the characters. So this is the character of V star tensor W. And because these are isomorphic representations, this is equal to the character of the representation Hom VW. Now this is nice, but by itself it doesn't give us too much information because Hom VW is just talking about linear transformations from V to W. The elements of these don't have to be representation homomorphisms, but really what we're interested in is representation homomorphisms. But we can actually get there using a little trick. Let's consider Hom VW superscript G. In other words, the subspace of Hom VW, which is fixed under the action of G as a representation. So what happens if we have an element phi, which is in Hom VW fixed space under G? If this is true, by definition, what that means is that G phi is equal to the original function phi. Now the question is, what is G phi? This comes down to knowing what this representation Hom VW does when we multiply elements of G. This element G times phi is given by the composition of functions G composed with phi composed with G inverse. So in this case, remember we're taking homomorphisms from V to W. So we start over here with an element of V. We multiply that by G inverse, then we apply phi that takes us over to W, and once we're in W, then we multiply by G. So when we say that G phi equals phi, we're saying G composed with phi composed with G inverse is the same map from V to W as phi. Now what I'm going to do is multiply by G on the right side here. And what we'll get then is G composed with phi equals phi composed with G. And now we recognize this equation down here. It's the equation for G equivariance or G linearity, or in other words, phi being a representation homomorphism. So we've just shown that if phi is an element of the fixed space of Hom VW under the action of G, then phi is a representation homomorphism from V to W. So in other words, it is a CG module homomorphism from V to W. So we've shown that these two spaces are the same thing, which means we have a way to take simple linear transformations from V to W and turn them into CG module homomorphisms. The reason this is useful is that it seems kind of difficult at first to get from C linear transformations to CG module homomorphisms, but we've just shown that we can get to a CG module homomorphism simply by finding a linear transformation which is fixed under the action of G. And we know how to get elements that are fixed under the action of G because we have a projection formula. We have a map for any representation that projects elements of that representation onto the fixed space. And the map is given by 1 over the size of G times the sum over all elements in the group of G. This map gives us a projection onto the fixed space. Now we know from linear algebra that the trace of a projection matrix equals the dimension of the image of the map. In this case, we are projecting onto the fixed space of the representation, which means the trace of this projection map equals the dimension of the fixed space Hom VW superscript G. And we can calculate the trace of this map. Because the trace is a linear operator, we can bring this to the inside. So this becomes 1 over the size of G times the sum over all elements in G of the trace of G. But by definition, the trace of the linear transformation described by multiplication by G is the same thing as the character of the representation evaluated at G. So we get chi Hom VW of G. And we found earlier a formula for this character. It's the same thing as chi V G bar times chi W of G. So this is equal to the dimension of the fixed space of the representation under the action of G. And we showed that this is the same as the space of CG module homomorphisms from V to W. So we just showed that this sum right here, which you might recognize as the inner product between chi W and chi V, this is equal to the dimension of the space of CG module homomorphisms from V to W. And we can get a little more information about this if we consider only the irreducible representations, because we know what the dimensions of these homomorphism spaces are between irreducible representations. So let's take a look at that now. What is the dimension of Hom CG from UI to UJ, where the UI index all of the irreducible representations of G? Well, we have two cases. First, suppose that UI and UJ are non-isomorphic. Schur's lemma tells us that any homomorphism between two irreducible representations is either 0 or an isomorphism. So if these two are not isomorphic, the only map between them is 0. On the other hand, let's suppose that these two representations are isomorphic. They're the same irreducible representation. Schur's lemma also tells us that the only CG module endomorphism from an irreducible representation to itself is scalar multiplication, and therefore this vector space has dimension 1. These are the two cases. So we just showed that this dim Hom CG UI comma UJ is 0 or 1 depending on whether the representations are isomorphic. And we just showed earlier that this dim Hom CG of UI comma UJ is the same thing as this sum down here, which we know is the inner product of the character of UJ with the character of UI. So this is equal to 0 if I is not equal to j, and it's equal to 1 if I is equal to j. And just like that, we've shown that the irreducible characters are orthonormal. So we got to the inner product by showing that this map gives us a projection from the space of simple linear transformations, V to W, onto the CG module endomorphisms from V to W. And the trace of this map is given by the character of that tensor product v star tensor w, which is chi v bar times chi w. And so we get that this inner product by Schur's lemma is always going to be 0 or 1 according to whether the indices of the irreducible representations are equal. So now that we've proved orthonormality, it remains to show that the irreducible characters generate every complex valued class function on G. To do that, we need to dive into class functions proper. So let's consider some class function alpha from the group G to the complex numbers. And for each class function, we're going to define a map which is given by 1 over the size of G times the sum over all elements of G of alpha of G times G. So this is a map for any representation V. This defines a map from V to itself. In particular, if we let Ui be the irreducible representations like earlier, we're going to consider this as a map between an irreducible representation and itself. Now, because alpha of G are scalars and G give linear transformations on every representation, this is definitely a C-linear map. But we also have, if H is an arbitrary element of G, H times 1 over the size of G, sum over all elements of G, alpha of G times G. We can bring the H to the inside, so we have alpha of G times HG. But we know that HG is equal to HG H inverse times H. So we can rewrite this as 1 over the size of G times the sum over all elements of G of alpha of G times HG H inverse H. Now, the key here is that alpha is a class function on G, which means that alpha of G in here is the same thing as alpha of HG H inverse. And we know that conjugation is a bijection on the elements of a group. So this sum in here is saying sum over all group elements, alpha of that group element times that element. This is the exact same thing as the original sum from earlier. So this is equal to 1 over the size of G, sum over all elements of G, alpha of G times H. So we've just shown that H composed with this map is the same thing as this map composed with H, which means that this map is not just a map from every irreducible representation to itself, it's actually a CG module endomorphism from every irreducible representation to itself. Now, by Schur's lemma, every representation endomorphism on an irreducible representation must equal a scalar multiple of the identity. So we know that this map is the same as lambda times the identity map for some scalar lambda. And if we take the trace of both sides here, we get lambda times the dimension of Ui equals 1 over the size of G times the sum over G in G of alpha of G times the trace of the map given by multiplication by G, which is the same thing as the character of the irreducible representation. Now, the first thing to notice here is that this sum with 1 over the size of G and then these elements on the inside is the same thing as the inner product of chi I with alpha bar. And the other thing to notice is we can solve for lambda if we divide by the dimension of Ui. So this gives us how every class function defined this way as a map on Ui acts on the irreducible representations. It acts as 1 over the dimension of the representation times the inner product of chi I with the complex conjugate of that class function. The key thing to realize here is that the action of this class function on every irreducible representation Ui is completely determined by the inner product of alpha bar with the irreducible character chi I. Now, to get the final part of the proof, we are going to turn to the regular representation. By Moshka's theorem, we know that every representation is a direct sum of irreducible representations, and therefore we can decompose the regular representation CG as the direct sum over at least some of the irreducible representations, ui to the power, let's say, direct sum mi. Now let's consider the action of this map defined by alpha on the regular representation CG. Because CG is a direct sum of the irreducible representations ui, the action of this map given by alpha is completely determined by its action on the irreducible representations ui. And in turn, the action of alpha on the irreducible representations is completely determined by the inner product chi I with alpha bar. Now let's consider the inner product of the irreducible character chi I with the sum over all irreducible representations of chi j inner product with alpha bar complex conjugate times chi j. Now, because the irreducible characters are orthonormal, the inner product of chi I with chi j is 0 for all I not equal to j. So this inner product is just equal to the inner product of chi I with the chi I term in the second part, which is the inner product of chi I with alpha bar complex conjugate times chi I. Now, the inner product of chi I with itself is 1, so all we have left is this scalar. Because this is a Hermitian inner product, a scalar in the second part of the inner product gets pulled out with a complex conjugate over it. So the final result is that we get rid of the bar, and we just get the inner product of chi I with alpha bar. So notice, the inner product of any irreducible character with this sum, this linear combination of irreducible characters, is the same as the inner product of that irreducible character with alpha bar. Remember that the action of a class function on the regular representation is completely determined by these inner products of chi I with the conjugate of the class function. So because the inner product of chi I with this sum is the same as the inner product of chi I with alpha bar, we can say that the action of alpha on CG, defined by this map, is the same thing as the action of the complex conjugate of this sum here, because remember, we're taking the inner product of chi I with the conjugate of the class function. So this is the same as the action of the conjugate of the sum over j of chi j with alpha bar chi j, and then we take the complex conjugate here as well. Now, this is a little bit of a monstrosity of complex conjugation. We can simplify it a little bit by noting that with a Hermitian inner product, we can switch the arguments if we remove the complex conjugate. So this is the same thing as the complex conjugate of the sum over j, but in here we take alpha bar with chi j instead. And that's going to get rid of one of those bars in there. I'm going to call this class function beta. When we say that the action of alpha is the same as the action of beta on this representation CG, we're talking about the action of the map given by 1 over the size of g times the sum over all elements of g of alpha of g times g. So we're saying that this is the same thing as that map defined instead using the class function beta. So if these two define the same map on CG, in particular, they have to give the same output if we apply them to the multiplicative identity of this ring, which is 1e. The thing is, these are not just endomorphisms on CG. They're more specific. These are actually elements of the group ring CG, and the map is defined by left multiplication. So the action of this element of CG on the multiplicative identity just gives us back that element of the group ring. So on both sides, we're just going to get alpha GG. And then on the other side, we'll get beta of G, G. So we've now concluded that these two are equal not just as maps on the regular representation, but as elements of the group ring. In particular, that means that the coefficient in front of each group element has to be equal on both sides. And the coefficient is given by the output of the class function on that element of G. So we're saying that the output of the class functions alpha and beta are equal on every single element of G. And that means that these two are, in fact, the same class function, alpha equals beta. So just like that, we're able to conclude that alpha is equal to beta, which we defined as the sum over j of the inner product alpha bar with chi j times chi j, and then that whole thing conjugated. Now, I'm going to simplify the expression on the right a little bit using two little tricks. First of all, I'm going to take the complex conjugate on both sides of this equation. So we'll get alpha bar, and then we'll get a double bar on the other side, which cancels out. And we're just left with the sum. And finally, we can substitute alpha with alpha bar. So if we substitute alpha with alpha bar everywhere in this equation, we're left with this final result. Alpha is equal to the sum over all irreducible representations of the inner product alpha with chi j times chi j. The part that's most important for us right now is that we've written every class function alpha as a linear combination of the irreducible characters. And from this we conclude that the irreducible characters generate all class functions on G. So let's go over a quick review of the entire proof. For orthonormality, we started with the observation that the map given by 1 over the size of G times the sum over all elements of G of the map defined by that element of the group gives us a projection from the space of linear transformations from V to W to the fixed space of that representation under the action of G. And we showed that that fixed space is the same thing as the set of CG module homomorphisms from V to W. Now the trace of a projection map equals the dimension of the image. So we can recover the dimension of the space of CG module homomorphisms from V to W using the trace of this map. Now with the isomorphism hom VW is isomorphic to V star tensor W, we can find the character of this representation. And taking the trace of this map using this character value shows that the dimension is equal to chi W with chi V. Now by Schur's lemma, we know that the space of CG module homomorphisms between two irreducible representations is 0 or 1 depending on whether they're isomorphic, and that gives us the result that these irreducible characters must be orthonormal. Next, we showed that every class function on G defines a CG module endomorphism on the irreducible representations. By Schur's lemma, that map has to be scalar, which means we can find it using its trace. And the trace is determined by this inner product of chi I with alpha bar. Because the regular representation is a direct sum of irreducibles, we know that the action of alpha on the regular representation is also determined by the inner products of chi I with alpha bar. But the map defined by alpha on the regular representation is itself an element of the group ring, and we know that two elements of CG give the same action on CG if and only if they are equal. And therefore we determine that alpha is equal to this sum of its inner products with chi j times chi j. And that gives us the result that the irreducible characters generate every class function on G. In short, the irreducible characters are orthonormal by Schur's lemma because the inner product of two characters gives the dimension of the space of CG module homomorphisms between the representations, and the irreducible characters generate every class function on G because the action of a class function on the regular representation is completely determined by its inner products with the irreducible characters.